Hi folks, welcome back to 9.5, the Binomial Theorem. So last time we were talking about this new notation and this formula to help us shortcut the binomial theorem, or binomial expansion. So instead of having to FOIL out everything, we could find the coefficients using this formula, okay? Or if we happen to have a Pascal's triangle handy, we could use the lines of Pascal's triangle to help us figure out the coefficients, okay? So let's take a look at 3 different examples on how to use the Pascal's triangle and the binomial theorem. All right, so we've got just an alternate way of writing Pascal's theorem, Pascal's triangle rather, using the notation we learned above, okay? Remember this top number here is your n and your bottom number is your k value, okay? But it's not a new chart, it's just very similar to the Pascal's triangle, just a different way of writing it, all right? So let's take a look at example 1. Example 1 says expand x plus y to the 10th. Now, I don't want to sit here all day and FOIL x plus y 10 times. So what I'm going to do is I'm going to use this exponent and I'm going to find the row in Pascal's triangle that has a 10 in it. Okay, so find row with 10. And I'm going to write out those coefficients, okay? So let's go back up, and I have my 5th line, 6, 7, 8, 9. 10 is the last line, okay? So let's go ahead and take these numbers. All right, so we've got 1, 10, 45, 120, 210, 255, and then the numbers go back down. And those numbers are going to be our coefficients. And other than that, all we need to do is make sure that we start with our a to the n, we end with our b to the end, and everything in between, the a's drop a power and the b's gain a power. Okay? So let's go ahead and do that. So I have the coefficients, let me write them out, 1, 10, 45, 210, oops, sorry, I missed one, 120, 210, 255, and then back down, 210, 120, 45, 10, and 1, okay? So these are my coefficients. Now, let's start with the first one. Okay, so the first one is a coefficient of 1, and it's going to be x to the 10th power. Okay. Technically, there's also a y to the 0 power here. But since y to the 0 equals 1, we don't write that term. Okay, let's keep going. Plus, the next coefficient is 10. X to the lose a power, so 9, and y to the gain a power, so 1. Okay, now that one we do have to write because y to the 1 is y. All right, so let's keep going. The next coefficient is 45. X to the 1 less than 9 is 8. Y to the 1 more than 1 is 2. Plus 120, x to the 7th, y to the 3rd. Okay, so I've used 1, 2, 3, 4 of them so far. Plus 210, y, x to the 6th, y to the 4th. All right. Plus 252, x to the 5th, y to the 5th. Okay. And then we can start to go back down. So plus 210, x to the 4th, y to the 6th, plus 120, x to the 3rd, y to the 7th, plus 45, x to the 2nd, y to the 8th, plus 10, x to the 1st, y to the 9th, plus 1 times, again, we don't write this one, but it's really x to the 0 and then y to the 10th. Okay? So that was a little bit of work. We certainly had to still match and keep track of whether we're adding or subtracting exponents, but it was a lot faster than multiplying this out 10 times. Okay? So this gives us our answer for number 1. All right, so let's try another example. Example 2, expand x minus y to the 7th. Okay, so 2 things here. We're changing the power to 7, so now we need to find the row that has 7 in it in Pascal's triangle. And we have a minus, which means we're going to need to make sure that our signs work out for this. Okay, so I'm going to go back up. I'm going to find the coefficients from the 7th line in Pascal's triangle. So we have 5, and this was 6, and so 7 is this one. So we have 1, 7, 21, 35, and then back down, 35, 21, 7, and 1. All right, so let me go back down. I'm going to write those coefficients out. All right, so I've got 1, I have 7, 21, 35, and then back down, 35, 21, 7, and 1. Okay, so when I expand this, I'm going to get 1x to the 7th, and remember there's an imaginary y to the 0. Well, not imaginary, but we just don't have to write it because we already simplified it. Plus 7x to the 6th, and then we're plugging in a negative y this time, negative y to the 1, plus 21x to the 5th, and then negative y squared, plus 35x to the 4th, and negative y to the 3rd, plus 35x to the 3rd, negative y to the 4th, plus 21x squared times negative y to the 5th, plus 7x times negative y to the 6th, plus 1. Remember, there's really an x to the 0 here, and this will be negative y to the 7th. Now, the reason why I put in the negative y's is because x minus y to the 7th is really the same as x plus negative y to the 7th. And when we write it like that, then we can follow the structure we have, okay? Now, again, you'll notice that some of these are going to become positive, like negative y squared is going to be positive, but some of them are going to stay negative, which is going to change the sign in between the terms. So if I simplify this, I'll get x to the 7th minus 7x to the 6th y, because that's a negative y, plus 21x to the 5th y squared, minus 35x to the 4th y to the 3rd, plus 35x to the 3rd y to the 4th, minus 21x squared y to the 5th, plus 7x y to the 6th, minus y to the 7th. This is our binomial expansion for x minus y to the 7th. Okay? All right, so let's take a look at one more example. And this one that we're going to finish off with is a little bit different because we have 2x that goes in for my a, and we have 3y that goes in for the b. But we're going to use the same coefficients because this is to the 7th. We just have to plug in different things. So the coefficients we're using are 1, 7, 21, 35, and then back down, 35, 21, 7, and 1. All right, so we're going to have 1 times 2x to the 7th. Remember, the 3y will be to the power of 0, so I don't really need to write it. Plus 7 to 2x to the 6th, and then 3y to the 1st. Okay, so I just have to take the whole thing and plug it in. I don't just plug in the x and then ignore the coefficient. I have to keep the 2 with the x and the 3 with the y. Plus 21 times 2x to the 5th, 3y squared, plus 35, 2x to the 4th, 3y to the 3rd, plus 35 times 2x to the 3rd, 3y to the 4th, plus 21 times 2x squared times 3y to the 5th, plus 7 times 2x to the 1st times 3y to the 6th, plus 1 times 3y to the 7th. And again, we don't really need to write that 2x to the 0. Okay. Now, as you can see here, our coefficients are going to be different than Pascal's triangle because the a and the b terms have their own coefficients. So instead of just being Pascal's triangle, it's going to be some multiple. So let's simplify. 2 to the 7th is going to give me 128. So my first term becomes 128x to the 7th. Plus 7 times 2 to the 6th times 3 will give me 1344x to the 6th y. Plus 21 times 2 to the 5th times 3 squared is going to give me 6048x to the 5th y squared. Plus 35 times 2 to the 4th times 3 to the 3rd will give me 15120x to the 4th y to the 3rd, plus 35 times 2 to the 3rd times 3 to the 4th will give me 22680 x to the 3rd y to the 4th, plus 21 times 2 squared times 3 to the 5th will give me 20412 x squared y to the 5th, plus 7 times 2 times 3 to the 6th will give me 10206 x y to the 6th, plus 3 to the 7th will give me 2187 y to the 7th. And that is how you use that binomial theorem in Pascal's triangle to help you expand a binomial without having to FOIL everything out. All right? So I hope this was helpful. Let me know if you have any questions, and I will talk to you soon.